Okay, I've made a list of topics which you can find on Blackboard, and I've uploaded test questions with solutions. And probably I will upload some more test questions during the Christmas holidays. I think I will make the exam next week. And then, okay. Well, let's, can you read it, or maybe it's too small? Okay. So what are the topics? Perspective drawing. And the thing we started with. You remember with three pieces, the parallel lines intersecting on the horizon. The union jack construction for the perspective view of a midpoint. Remember, it's of course related to harmonic quadruples, something you asked about. The topology of P1, it's a circle, at one point at infinity and minus infinity, and you glue those minus infinity to plus infinity. We've looked at the topology of the projective plane. So it's a disk and a Möbius strip. Just the knowledge, I think, is enough. Parabolas and hyperbolas in perspective. Also, during lecture number 7, the first lecture of the second lecture series, I handed out this kind of spare paper in perspective, and you had to draw hyperbolas, parabolas. And there we saw for the first time that, for example, a parabola touches the line at infinity, touches the horizon. At that point, it was kind of intuitive, and it was related to drawing in perspective. And later, that was our definition of a parabola in affine geometry. And hyperbolas, we saw a hyperbola intersects the line at infinity in 2 points. And those are exactly the points where the asymptotes intersect the line at infinity. And in fact, the asymptotes are tangents at infinity. That's an important thing, because you need that if you translate from a projective theorem to an affine theorem, which is something which would certainly appear in the exam, which is also in the test. Asymptotes tangent at infinity. Yes, the thing we did all the time. So given a projective statement, I say, well, we take this line as the line at infinity, and you now state the affine. Maybe we should.
Yeah, you have a couple of questions already in the
test exam. We can look at
changing perspective.
Yeah, there are many examples. Of course, the definition of the projective space. I did it for an arbitrary vector space. It's a set of lines through the origin. Pn, you have to be careful. Pn is n-dimensional projective space, so it belongs to the vector space P is R n plus 1, one-dimensional item. Okay? We've looked at this. This is about the relation between P2 and R2. So it's R2 is, you have to choose a line at, which is line at infinity. Going back and forth. Homogeneous coordinates. Well, we've considered points, lines, and conics. So this is a linear equation, quadratic equation. Duality, we will do an example. I suggest we look at Pappos, because we didn't dualize Pappos. It was a homework exercise. Maybe we do it. Yeah? Those are theorems, you just have to know them. Yeah? And of course, I could ask you to prove it. And then there are several ways to prove it. Either you choose homogeneous coordinates, suitable homogeneous coordinates. You remember, if you have 4 points in general position, then there are special homogeneous coordinates. And that makes life easier. We proved Pappos that way. It was in the slides. And you could prove Desargues the same way. So that's one way, using homogeneous coordinates. Another way is choose a suitable line at infinity and reduce it to some special statements about parallel lines. We did that with Desargues. I know that Desargues, in a very special affine case, is one of the exercises in chapter 1 in Stillwell, you remember? And Pappos also? Okay.
Yeah, it's one.
So this reduction step you should be able to make. And so then there are two steps. One is the reduction step of the projective theorem to an affine theorem, a special case, which for me is an important thing. And the other step is to actually prove this statement in affine geometry, which for me is slightly less important now.
I think
Going back and forth between projective and affine geometry, that's the main topic. Yeah.
Please summarize for me the ways of proving the theorems.
Okay.
Just mention them at the
Two. So one is choose convenient homogeneous coordinates. The way what we did for Pappos in the lectures. Yeah. I did it, I think, in lecture number 5 or 4. Well,
This
plus
series.
6, of course. Yeah. 10 or 11. And then I said the second half is homework.
Yeah, that was in 11.
And in the next lecture, I had the slides where you see all the answers appear.
Yeah.
So you have an example of that. And a good test is to try and prove this R that way. We could make a star if you want. That's one way, coordinates. And the other way is choose a smart line as the line at infinity and reduce it to a special affine statement.
I guess at the exam you will explicitly state, well, prove it in...
Yeah, I can do that. Yeah. But you have to know those two methods. Yeah?
Might not be the case.
I will probably say do it that way. Okay. We can do some examples. Convenient homogeneous coordinates. So given 4 points in general position, there are homogeneous coordinates such that they have coordinates 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 1. Yeah. It's an important theorem. It's even called the fundamental theorem in projective geometry. Really important. But it's important if you compute in homogeneous coordinates. That's a good first step. Makes life easy. Yeah. So it is similar to what we are used at in Euclidean geometry. Then you say, well, I can assume that this is the origin, and I can assume that this is 1, 0. Then you have only 2 points which you can choose. Now you can choose 4 points, provided they are in general position, which shows that projective geometry is easier. The group is much larger. Yeah. So number 11 is, of course, terribly important. Yeah. Making an F perspective view. So it's the same thing, I think. Oh, know that they are equivalent, and this is actually making this translation. And then the next notion is cross ratio. There are 2 definitions. Stillwell has a definition in inhomogeneous coordinates. And I gave a definition in homogeneous coordinates. And we saw during the lecture that they are equivalent. Why are cross ratios important? Well, because of this. They are invariant on projective transformations.
Say again, what do you different?
In Stillwell, the definition is inhomogeneous. In inhomogeneous coordinates. And I gave a definition in homogeneous coordinates. Yep. And they are equivalent. Of course, cross ratio is invariant on a projective transformation. So in particular, they are invariant under under projections. If I project from a point from one line to another line, the cross ratio of these 4 points is the same as the cross ratio of these 4 points. It's fundamental. Okay, then
Spandaw definition is much more important, I think.
More famous, at least.
More famous.
it's certainly better. So if I have this one, yeah, if I have this true or false question, you know which is more. Yeah.
How can two things that be both be true be better than one?
Okay. 14. That's my definition. That follows immediately from my definition of the cross ratio. So we know that cross ratio can take any value but 0, 1, and infinity. So it's a projective line minus 3 points. It's magic. Yeah. The behavior, what happens to the cross ratio if you produce the points? Well, there are in fact 24 permutations, but we only need these 4. I think. So we never, if we have 2 pairs, we never considered the case when we only changed within the pairs, so swap 2 within a pair or swap both pairs, but we never said, well, let's take one element of one pair and another element of the other pair and swap those 2. You can do that, but we never did that. So I won't ask that. Harmonic quadruples, you asked about it, we will look at that. Conics, yeah, conics is something which I think is not in Stillwell. Quadratic equations. So ellipses, hyperbolas, parabolas. Well, the classification, the important thing is that you know that there are interesting conics and uninteresting conics.
And you can Google that, interesting one.
Yeah. And interesting conic. So the official name is a real, non-empty, non-degenerate conic. Non-degenerate means that it is not the product of 2 lines. But interesting is shorter. Okay. Then this hierarchy, we will look at that because of your question. The corresponding transformations, we will look at that too. Yeah. Then we have this strategy, if you prove a theorem, step number 1 is to determine how fine or how coarse the structure is. And the coarser the better, because then you have more freedom to make life easy for yourself. So you have to recognize, well, projective notions. Suppose you have a statement where all notions are projective, then you are really lucky because you can do almost anything to it. So you have to, point, line, conic, instance, tangent, all these notions are projective. Yeah? Yeah.
You did it on the blackboard, on that board, all these.
Yeah, it's also in the slides. I added a few slides in.
Okay.
So there are lists in the slides. Pretty, I think pretty complete. Yeah? Okay.
What's the fourth harmonic?
The fourth harmonic, yeah. The fourth harmonic is the following. So suppose that this cross ratio is -1. Yes, suppose this cross ratio is -1. Then we know that they alternate. A pair AB separates a pair CD. So you can, if you have 3 points, then there is no way of saying that one of the points lies between the other 2, because projective line is a circle. But if you have 4 points, then you can say that they alternate. Yep. Okay. That means that cross ratio is negative. Okay, if we have this, and who asked the question about fourth? Okay, you choose one of the letters A, B, C, D. A. Okay. Then we say that A is the fourth harmonic point of B with respect to C and D. That's the fourth harmonic. So it's the solution of this. It's the solution of this question.
You can deduce A from B, C, and D.
It's called the fourth harmonic. Yeah.
You need 3 variables solve the last.
So one of the ways of saying it is the fourth harmonic of B with respect to C and D is the perspective view of the midpoint of the line segment CD with respect to the vanishing point B. Yeah. This is the perspective view of the midpoint of CD with respect to the vanishing point B. So B is the point at the horizon.